Welcome back. In this video, we're going to have an introduction to types. So a very basic question to ask is, what is a type anyway? And this question is worth asking because the notion of type, what a type is, does vary from programming language to programming language. Now, roughly speaking, the consensus is that a type is a set of values and also, and perhaps more importantly, a set of operations that are unique to those values, a set of operations that are defined on those values. So for example, if I look at the type of integers, there are some operations that you can do on integers. You can do things like you can add and you can subtract integers, and you can compare integers, whether they're greater than or equal or less than. Okay, and then these operations are, you know about numbers. And then there are operations on strings. And strings are a different type. They have operations like concatenation and testing whether a string is an empty string or not. And there's a variety of other functions that are defined on strings. And the important thing is that these operations are different from the operations defined on integers, and we don't want to mix them up. It would be bad if we started doing string operations on integers, for example. We would just get nonsense. So in modern programming languages, types are expressed in a number of different ways. In object-oriented languages, often we see classes being the notion of type. So particularly in Cool, the class names are the types. They're all, with one exception, called self-type, the class names are exactly the types. And I just want to point out that this need not be the case. It happens that it's often convenient in object-oriented languages to equate classes and types, but there are other designs where the classes are not the only kinds of types, or whether they're and in some languages where there's no notion of class, the types are completely different things. So classes and types are really two different things that happen to be identified in a lot of object-oriented language designs, and I just want you to be aware that that's not necessarily the only way to do it. So consider the assembly language fragment add R1, R2, R3. And what does this actually do? Well, it takes the contents of register R2 and the contents of register R3, it adds them together, and it puts the result in register R1. And the question is, what are the types of R1, R2, and R3? And you might hope that they're integers, but in fact, this is a trick question because at the assembly language level, I can't tell. There's nothing that prevents R1, R2, and R3 from having arbitrary types. They could be representatives of any kind of type, and because they're just a bunch of registers with zeros and ones in them, the add operation will be happy to take them and add them up, even if it doesn't make sense, and produce a bit pattern that it stores into R1. So to make this a little clearer, perhaps, it's useful to think about certain operations that are legal for values of each type. So for example, it would make perfect sense to add two integers. If I have two bit patterns that represent integers, then when I sum them up, I will get a bit pattern that represents the sum of those two integers. But on the other hand, if I take a function pointer and an integer and I add them together, I really don't get anything. This is the function pointer is a bit pattern, the integer is a bit pattern. I can take those two bit patterns, I can run them through an add, and I do get out a new set of bits, but there is no useful interpretation of that result. The resulting thing I get doesn't mean anything. But the problem is that both of these have the same assembly language implementation. Okay, nothing at the assembly language level, these two operations look exactly the same. So I can't tell at the assembly language level which one of these I'm doing. And if I want there to be types, if I want to make sure that I only do operations on the correct, that I only do certain operations on their correct types, then I need some kind of type description and some sort of type system to enforce those distinctions. So perhaps I'm belaboring this point, but I think it's important. So one more time. A language's type system specifies which operations are valid for which types. And then the goal of type checking is to ensure that operations are used only with the correct types. And by doing this, type checking enforces the intended interpretation of values because nothing else is going to check. Once we get down to the machine code level, it's all just a lot of zeros and ones, and the machine will be happy to do whatever operations we tell it to on those zeros and ones, whether or not those operations make sense. So the purpose of type systems is to enforce the intended interpretations of those bit patterns and make sure that if I have a bit pattern for integers that I don't do any non-integer operation on that and get something that is meaningless. Today, programming languages fall into three different categories with respect to how they treat types. There are the statically typed languages, where all or almost all of the checking of types is done as part of compilation. And Cool is one of these, and other languages that you've probably seen, like C and Java, are also statically typed. Then there are the dynamically typed languages, where almost all of the checking of types is done as part of program execution. And the Lisp family of languages, like Scheme and Lisp itself, are in this category, as are languages like Python and Perl. Right? And so you probably used or heard of at least some of those languages. And then finally, there are the untyped languages where no type checking is done at all, either at compile time or at runtime. And this is basically what machine code does. So machine code has no notion of types and enforces no abstraction boundaries when it executes. For decades, there has been a debate about the relative merits of static versus dynamic typing. And without taking sides, let me lay out for you what the various proponents on each side say. So the people who believe in static typing say that static checking catches many programming errors at compile time, and it also avoids the overhead of runtime type checks. If I've done all the type checking at compile time, well, I don't have to check the types at runtime. I don't have to check when I go to do an operation that the arguments are of the correct type because I already did that check once and for all at compile time. And these things are both definitely true. These are the two big advantages of static checking. First of all, it proves that some errors can never happen. Those are caught at compile time, and so I never have to worry about those errors at runtime. And also, it's faster. Dynamic typing proponents counter that static type systems are restrictive. So essentially, a static type system has to prove that the program is well typed, that all the types make sense. And it does this by restricting what kinds of programs you can write. There are some programs that are more difficult to write in a statically typed language because the compiler has a hard time proving them correct. And there's also a belief that I see commonly stated that rapid prototyping is more difficult with a static type system. And I think the idea here is that if you're prototyping something, if you're exploring some idea, you may not actually know exactly what all the types are at that point in time, and having to commit to something that's going to work in all cases, to having a type correct program when you're just trying to fiddle around and figure out what it is you're trying to do, that's very constraining and makes the work go quite a bit slower. So what's the actual situation in practice today? Well, an awful lot of code is written in statically typed languages, and the practical statically typed languages that people use a lot always have some kind of escape mechanism. So in C and Java and C++, you have some notion of unsafe cast. In C, an unsafe cast can just result in a runtime crash. In Java, it results in an uncaught exception at runtime when you have an unsafe or a failed downcast. But the effect is that you can get runtime errors for type reasons. Now, on the dynamic typing side, the people who program in dynamic languages, they always end up or seem to end up retrofitting static typing to these dynamically typed languages. So typically, if a dynamically typed language becomes popular enough, then people start trying to write optimizing compilers for them. And the first thing that people want to have in an optimizing compiler is some type information because it helps to generate much better code. And so people wind up going back and trying to figure out how to get as many types as they can from these dynamically typed languages as soon as they start trying to build serious tools to improve the programs written in these languages. And in my opinion, it's really debatable whether either compromise, because both of these are compromises on the either strict static or strict dynamic point of view, whether either one of these represents the best or the worst of both worlds. But this is certainly where we are today in practice. Now, Cool is a statically typed language, and the types that are available in Cool are the class names. So every time you define a class, you define a new type, and the special reserved symbol self-type, which we'll be talking about in a separate video all of its own. And the way Cool works is that the user declares the types for identifiers. So for every identifier, you have to say what its type is. But then the compiler does the rest of the work. The compiler infers the type for expressions. And in particular, the compiler assigns a type to every single expression in the program. So we'll go through the entire abstract syntax tree, and using the declared types for identifiers, it will calculate a type for every expression and sub-expression. To wrap up, it's worth mentioning that there's a couple of different terms that people use for the process of computing types, and that they mean slightly different things. So the simpler problem is what is known as type checking. Here we have a fully typed program, meaning we have an abstract syntax tree with all the types filled in on every node, and our only job is to check that the types are correct. So we can just look at each node and its neighbors and confirm that the types are correct in that part of the tree, and we can do this for every part of the tree and check that the program is typed correct. Type inference, on the other hand, is the process of filling in missing type information. So here the view is that we have an abstract syntax tree with no types on it, or perhaps just a few types in key locations on it, say on the declared variables, and then we want to fill in missing types. We have some nodes in there with absolutely no type information at all, and it's not just a question of confirming or checking that the types are correct. We actually have to fill in the missing type information. And these two things are different. Actually, they're actually in many languages they're actually very, very different. But people often use the terms interchangeably, and I will not be particularly careful in my videos about which term I'm using either.